This is a conversation with Tim Maudlin. He's a professor of philosophy at New York University, the author of multiple books on the foundations of physics, and the founder of the John Bell Institute. In this conversation, we discuss the foundations of physics, the philosophy of physics, the importance of mathematical structures, and the limitations of language in science. And then we talk about John Bell, Bell's theorem, Bell's inequality, the implications it had on quantum physics, locality and realism, all the fun stuff. And we also talk about the concept of time. This is no time. If you like what you see, then do hit subscribe on YouTube, follow on Spotify, or rate 5 stars on Apple Podcasts. This project takes a lot of my time, money, and efforts. If you'd like to see it continue, do consider making a donation on Patreon, buying thanks on YouTube, or becoming a member, or making a donation on Instagram. If not through monetary support, then do consider sharing these episodes, leaving your likes and comments. All forms of engagement, they really go a long way. For other forms of love and support, you can follow this channel on Instagram or Twitter, or follow me personally. And now, it's no time. In his book, Nouvelle Perspective and Microphysique, you'll have to pardon my French, Louis de Broglie said the following words: "Science itself, no matter whether it is a search for truth or merely the need to gain control over the external world, to alleviate suffering or to prolong life, is ultimately a matter of feeling, or rather of desire. The desire to know or the desire to realize." So I want to start by asking you the same question de Broglie asked himself. What feeling does science satisfy in your life? What desire to know or desire to realize does it satisfy? Why did you leave the super exciting fields of civil engineering and architecture and design and gravitate more towards philosophy, physics, and science in college?
Well, yeah, I mean, that's de Broglie sets it up in a perfectly good way. People can have different motivations or things that deeply attract them. As it turns out, I was most deeply attracted just out of curiosity to try and figure stuff out.
Yeah.
When I was very young, it was the 60s. There was a lot of ferment, social ferment. There was the Whole Earth catalog and Buckminster Fuller. I mean, this is the stuff I grew up with, of people who also had very practical ends, right? Wanted to change the world in very practical ways. And I was attracted to that to some degree, but at the end of the day, I also just wanted to figure out what's going on. And in a way that's completely impractical, in a way that probably has no particular impact on people's lives. I'm just curious, right? I'm just nosy. Yeah. And that's what won out over the more practical things.
You brought up Buckminster Fuller. We have to go there now. Buckminster Fuller once said that you never change things by fighting the existing reality. To change something, build a new model that makes the existing model obsolete. You have a very interesting origin story. You grew up in a house of contemporary design. You grew up heavily influenced by Buckminster Fuller, Frank Lloyd Wright. And it's interesting to me because both these gentlemen, Fuller, Frank Lloyd Wright, they were so radical. They challenged convention so often. They were pioneers in their own way. Do you think the fact that you started off with an interest in architecture, design, and civil engineering, do you think that unlocked a way of thinking, and the work of these people also unlocked a certain way of thinking within you, where you developed this framework for challenging conventions and norms, which you then brought into physics as well?
Actually, I think it did. My brother became an architect. My daughter got a degree in architecture, and she didn't grow up in the house I did, but she grew up in the house that we re-engineered, and my brother designed part of, and we designed part of. And I think just having your everyday environment be very, very different from what's standard. So you go to other people's houses, and most of them, they look kind of alike. And you kind of say, well, why is it laid out that way, right? Yeah. Why did you do that rather than this? Yeah. So it does open up, it opens up your mind to how arbitrary a lot of convention is. And that, of course, opens up your mind to thinking, well, how else could it be done? Maybe there's a better way to do it. And in the case of architecture, it's clear there are better ways of designing than the average American house. It's astonishing to me how much money and so on is put into building things and how little is put into the design of them. Most houses aren't designed at all. You just they're pre-built, or you grab some book of standard specs. And I can't really understand that. Whenever we've had a place, we've said, what do we want to do with it? And you try and think through, well, how do we want these spaces to flow into each other, and what are they for? And there's the old Louis Sullivan form follows function. I do think actually that has probably a deep psychological effect, and a salutary one, just that you have a slightly outsider view. The other thing that's very striking when you do it, when I bought the first house we had, and we redesigned it and modified it in various ways, the first time you take a sledgehammer to a wall, to a standard plasterboard wall, and it goes right through it, and you say, wait, that's not very solid, is it? It's not very hard to punch a hole in that. It's not very hard to take this out. Because you're used to thinking of architecture as very solid and impenetrable and immovable. And when you see how easy it is to move some of it, you have to be careful. You have to understand what's load bearing and what isn't. But it does open up your mind a little bit.
It's so fascinating to me, the type of influences you have in your childhood and how you translate that into your work later in life. We were talking about how you translated that framework, that style of thinking, into the work that you do. So let's address that formally. You have often described foundations of physics as an orphan in science. So let's define it first. What are the foundations of physics? What is the philosophy of physics? And why do you call it an orphan?
Okay, so the idea of foundations of physics is pretty simple. By foundations, one means what's going on physically at the most fundamental level, where there's nothing sitting below that. So, for example, if you're trying to understand DNA, there's a lot of chemistry, and you can say, look, we figured out that really it has this double helix structure, and this is how these things bind to each other. And that's all very important and gives you a lot of insight. But of course, you can always ask, but how is that double helix made? I mean, how do all the carbons and hydrogens stick together? What keeps them together? And then that pushes you down from chemistry down into physics. And also in physics, there's the physics of, solid state physics. There's all kinds of things you can do in physics about particular states of matter or particular systems, astrophysics or whatever. Yeah. But at the end you say, but at the bottom, that's all the same fundamental physics working its way through some particular situation. You go back to Democritus, and Democritus says that all there is atoms in the void. And, that's not, in a way, not very detailed, but it's very foundational, right? Everything else you're going to understand by saying, well, you've got different shaped atoms and they're moving around in the void, and maybe this one hooks up with that one, or this one bounces off that one. And everything we see at everyday scale is just all that going on at micro scale. That's part of physics. It's not all of physics. There's lots of physics you can do without being terribly concerned about the foundational structure. Yeah. But if you're like me, as I said, and you're just curious and you're just nosy and you just have this, childlike, but why repetition that keeps driving you, it'll drive you eventually down into foundational questions. What is there fundamentally? And this was always thought to be a basic part of physics. Yeah. The real problem occurred because of quantum mechanics, where there was a very sustained effort to tell people, stop asking these questions, or these questions can't be answered, or they can't be answered in ways you can really understand. Or Bohr was very, very strong on that line of the reason you feel dissatisfied with quantum mechanics is that we've gone beyond the realm where the human mind can really understand. And Einstein was very upset with Bohr because he says, what makes you say that? Why are you giving up? There's no reason to give up. Keep going, right? And you're really being satisfied with things that are quite clearly flimsy and unacceptable as basic postulates. There's a nice letter somewhere where Einstein talks about how quantum mechanics has created this pillow where physicists can sleep and it's very hard to wake them up. And he says, well, let's just let them sleep, because for decades he was saying there's something ill-defined about this theory. And as a physicist, you shouldn't be satisfied with it, not as a philosopher or something like that. And then you say, why is it an orphan? Well, because it should be done in physics departments, and it isn't. And it isn't because of Bohr and because of what happened with quantum mechanics. And all of these questions got sort of sidelined or shunted away or became impolite. And then the people interested in them, some of them drifted off into other places like philosophy departments, where philosophers are happy with questions like that. That's the questions they're most interested in. So it can take some root there, but it's still very scattered. People are just scattered over the world. They're scattered in different departments. There's very little that's institutionally constructed to support these kinds of inquiries.
So many things I want to explore here. You spoke about how you want to ask the most fundamental questions. You want to be nosy in a way. And there was this sustained effort after Bohr and the Copenhagen interpretation where these type of questions are not encouraged. You've shared a story from your life where I think in undergrad you had signed up for your first quantum mechanics course and you had raised your hand in the first class to ask a question about the foundations of physics. And the professor immediately shot it down in an attitude that pretty much said, shut up and calculate, right?
Yeah, well, yeah, it wasn't the first class. I mean, actually, this was in the middle of the class. I mean, we'd done quite a bit. And we were learning spin and you learned these matrices and how to, mathematically manipulate these matrices and so on.
Yeah.
So it certainly didn't come up in the first day of class because they wouldn't bring it up. What's really going on? I mean, from the beginning, it's here's a bunch of math, here's how to solve a Schrodinger equation. Here's what an eigenvalue is.
Yeah.
Here's how to manipulate that to make predictions, all the standard stuff. The standard stuff doesn't put you even in the mood to ask these questions. But it was in the middle of the class and we were talking about spin and the effect of magnetic fields on particles with spin. And I was trying to form a very concrete physical picture in my head of what was going on. And so I just put up my hand and said, is it like this? And sort of described this picture in my head. And it was at that point he said, no, it's not like that. And then didn't, as I say, he didn't go on and say, think of it this way. Think of it, here's a better picture. It's like, no, there's no picture. There's no comprehensible way to grasp what's going on here. Just get on with the calculation. And what can you do? I mean, if that's what your professor says, you're dissatisfied.
Yeah.
And this is absolutely common. I mean, I teach philosophy of physics all the time, and we get philosophy students and I get physics students. And it's just very common for the physics students to say, this is what interested me in physics. This is why I went into physics, was to ask these questions. And I'm not getting this in my regular classes. This is just commonplace. It's not anything that's questionable or, outrageous to say. Any physicist, anybody who's gone through a physics education will tell you that. I just gave a talk in Johns Hopkins, and it was about Bell's inequality. We'll get into that and so on, and kind of an exposition of it. And after the talk, a guy put up his hand. He said, I have a training in astrophysics, and none of this was ever explained to me. I mean, that's all he said. He said he wasn't objecting or anything. He just said, I learned quantum mechanics. I learned this. Nobody mentioned this. Nobody explained this. And you're saying, well, that's the way it is. Somebody ought to be doing it.
Why do you think that is? Like, if we had to dissect this shut up and calculate phenomenon as a case study and track its evolution, you've often mentioned that historically physics and philosophy was the same thing. Aristotle was a philosopher. You've said Isaac Newton would have considered himself a philosopher. So how do we get here from that synonymous coupling between physics and philosophy being the same thing to now this clear deviation where you have the shut up and calculate mindset on one side and you have philosophy on the complete other side?
You really have to trace it to quantum theory. If you look at the modern physics, even go before Einstein, so somebody like Maxwell or somebody like Boltzmann, these people were again asking exactly these foundational questions. I mean, Boltzmann was a committed atomist, and at the time, atomism was not accepted generally. And then he said, well, if in fact particles are, matter is made of atoms, if gases are atoms, what'll happen? How should they behave? How do they bounce? What can we show about what their behavior should be? And worked out a lot of thermodynamics that way. And Maxwell and the early people working in electromagnetic theory all of a sudden said, gee, we need to introduce these new objects, fields, electric fields, magnetic fields. They're not like anything that Newton ever thought of. But look, we can introduce them. We can write down some equations. We can see how they behave. We can connect up that behavior. You can now make radios and so on. Special and general relativity can also be understood as just very clear postulates about the fundamental structure of space and time. And general relativity is providing you a different account of gravitational phenomena, but one where you understand what the theory is claiming. I mean, in this respect, although many people think of both relativity and quantum theory as somehow mysterious, the situation is entirely different, because the more you work with the general theory of relativity, the better you understand it. The people who are really experts in that, you ask them a clear, concrete question, they'll give you a clear, concrete answer. According to the theory, this is what's going on. This is how to think about it. Mm-hmm. Whereas in quantum theory, the standard physicist has no answers if you ask, what is this theory really claiming? And again, my psychological hypothesis is it's kind of embarrassing to be a professor, and when a freshman asks you a perfectly good question, you have to say, I have no idea. So it saves face a bit better to say, that's a bad question.
Right.
Right? The problem isn't me, it's you. And this was more or less what Bohr was saying. You're asking for something that cannot be given. We've reached the limits of comprehension in a certain way. It's not true. What Bohr said is demonstrably untrue. You can do lots of things he said couldn't be done. And there are these the famous impossibility proofs we'll probably get into of von Neumann, a great mathematician telling you something can't be done. And then you wake up one day and say, hey, it can be done. Look, here it's been done.
Yeah.
So this idea of trying to squelch these questions, as far as I can tell historically, absolutely traces back particularly to quantum mechanics. Now, the irony is at another level, and this maybe for the last 50 years, many physicists have gone way off the deep end in pure untrammeled speculation about string theory and this and that, where they're perfectly happy to say things that sound like things Bohr would say. You can't even say that. Yeah. And then they just go way off into kind of mathematics and piling one thing on another. But at the same time, if you ask them basic questions just about quantum theory and how to understand it, they won't have clear answers to it. So it's a weird situation now.
I have to ask you another follow-up question about this shut up and calculate phenomenon about mathematical objects. This current physical system that we have can be ascribed by a mathematical object known as a wave function. There are different schools of thought around the significance of it. There's a school of thought that says the wave function is just representational of a physical structure. There's another school of thought that says the wave function itself is fundamental, or mathematical objects or structures are fundamental. This is something Max Tegmark also talks about. The universe is mathematical. Mm-hmm. There's cubism, there's number theory, there's Einstein's interpretation of these being statistical averages. Where do you stand on this? Do you think mathematical objects are fundamental in nature? Are they representation of physical structures, or is there something else entirely?
Well, mathematical physics is a field where mathematics is used as a representational tool, right? As a piece of language, if you will. Yeah. I'm going to use mathematical objects in an attempt to represent the physical world. Yeah. And those mathematical objects can be used in lots of different ways. So there's not one single answer to what does this piece of mathematics indicate about the physical world. If you just open up a physics textbook, you have to then look in great detail, where did this mathematical object come from? Yeah. Sometimes, as Einstein, as you say, wanted to understand the wave function statistically, that it's a kind of representation, sure, but it's a representation fundamentally of large collections of systems and telling you about their statistical characteristics, right? A certain percent are like this, a certain percent. This is what happens in thermodynamics. Yeah. We understand how to do that. And then you say, okay, so this mathematical object is not a representation of any single system. It's a representation of a collection of systems. And if I take this single system and move it from this collective to this collective, a different representation might be relevant now because I'm actually looking at a different system. That's the way Einstein wanted to think about the probabilities in quantum mechanics. So that's the so-called statistical interpretation. I can't make head or tail out of Max's idea that fundamentally physics just is mathematics and every mathematical object is a physical object and every mathematically representable possibility is a real physical world. As if, yeah, there is a real physical world somewhere that's Newtonian because you can write down Newtonian mechanics as some differential equations. I can't make it, I mean, just can't make head or tail out of that. There are some objects or elements of physics that we represent mathematically, and we think it's because they actually have a physical structure which is being very directly represented by the mathematics. So Euclidean geometry is a perfectly clear, abstract mathematical structure. You can ask all kinds of questions about objects in Euclidean geometry and get, really surprising answers. The example I always like is the one that Kant used actually, is that something that Euclid proves is that if you take a circle and put any two chords in it that intersect, so I'm just going to draw some straight lines across it, but they have to intersect.
Yep.
So this line gets cut into two pieces. This line gets cut into two pieces. Now, from these two pieces, make a rectangle. From these two pieces, make a rectangle. Those two rectangles will always have the same area. And you're going, wow, that's cool. That's a fact about Euclidean geometry. Does it follow that anything in the physical world has the structure postulated by Euclidean geometry? No, it doesn't follow at all. We know that at macroscopic scale, the space we are moving around in is pretty close to being Euclidean. We know that because we use Euclidean geometry to do surveying calculations, and it works really well. Doesn't mean it's perfect, right? There could be deviations at very fine levels. So there's something in the physical world that is very nearly well represented, at least by Euclidean geometry. Maybe there's something in the world that's exactly represented by Euclidean geometry. That would be interesting. And that would immediately explain the utility of Euclidean geometry in doing physical things. Or maybe the world is not fundamentally Euclidean at all, but there's an explanation for it has a structure that is in some well-defined sense close to Euclidean, at least at everyday scales, right? That would make sense. To say that physical space is just a mathematical object, to me, that doesn't make any sense, right? It may have a structure that's well represented mathematically, but that's different from saying it is simply a mathematical thing. So I would take that off the table. The other thing that people have said about the wave function, this is what the QBists are on about, is the idea, look, the wave function doesn't represent the physical structure of anything at all. The way Chris Fuchs used to say this is that if I have a wave function, suppose if I try to ascribe a wave function, I don't know, let me say to this thing.
Yeah.
I shouldn't stick the wave function on this. I should stick it on my head, because what that wave function represents isn't anything about this. It's about my knowledge or information or internal representation or something. It's a subjective thing. That can't possibly be right, because there are physical effects like interference effects, two-slit experiment, and things like that require there to be something in the physical world that behaves pretty close to the way these wave functions are, mathematically behave. And what's going on in my head isn't going to cause spots to form on a screen in a certain way, right? It isn't. So that can't be right either. The wave function has to represent something physical, and you want to know, okay, what is that, and how does that work? Now, it turns out that to me, all of the serious attempts to understand quantum theory that we have presently agree that the mathematical wave function represents some real physical item. Then there's a debate about whether it represents everything, whether it's complete, whether the wave function captures all of the physical structure. Some people, many worlds people usually try to argue that. Other people, the so-called hidden variables people, argue the opposite. Some people are a little unclear if you ask them that question. It's a clear question, so they should have an answer to it, but you'll find some people can't give you a straight answer. And that's, again, the kind of thing you should be concerned about. But I think it's absolutely clear there is some physical correlate, as it were, to the mathematical wave function. The curious thing about it, and this is unique to quantum theory, is because of the structure of quantum theory and entanglement and things we'll probably get into, it seems as though at a physical level, there really should only be one of whatever this is, and that should be the universal one. And that's very different than, say, in Democritean atomisms. Okay, there's an atom here, it has a particular geometrical shape. There's another atom here that has maybe a different geometrical shape, and you can't tell, you can specify this one completely without mentioning that one. You can specify this one completely without, So, but it looks like the only reasonable way to proceed here is to think that, yes, there's something that corresponds to the mathematical wave function, and furthermore, there's only one of it, and furthermore, that's the universal one.
The theory of everything?
Well, that's not the theory of everything. The theory of everything means a theory that covers all the forces and all the phenomena. I'm just talking about in any quantum theory, whether suppose it's a quantum electrodynamics, that's not supposed to be a theory of everything because it doesn't contain the strong nuclear force and so on, but it still has a wave function. In anything that looks like quantum theory, you're going to have something like a wave function. And if you think about it, at the end of the day, at a fundamental level, there ought to be only one, the universal one, which then the question arises, which is a really nice question. And you say, yeah, but I don't know what that is, right? I have no idea what the universal wave function is. But I can use quantum mechanics on small objects, on small subsystems. And I do that by ascribing the little subsystems their own wave function. So in the literature, people who talk about this, there's like capital psi, which is the universal wave function. That's the one real one. Yeah. But that's not what we ever use. We always use little psi, something we ascribe to subsystems. Mm-hmm. And that raises a really nice question, which is, well, where do these little psi's come from? They're not separate from the big psi. They somehow have to emerge or be definable from the big one and something else. This is something that in the pilot wave tradition, you can do very cleanly. You can give a really lovely account of how that works. And in other traditions, not at all so clear what's going on, how to understand it. So these are the kinds of questions that just come up immediately when you do this foundational digging and you say, okay, tell me what's at the very bottom of your theory, right? What are you postulating in your theory that isn't derived from anything else? And how do I get to something like the everyday world? And how do I get to the way this theory is used in the everyday world to make predictions, which it does very well, from those fundamental postulates? Those are just clear questions that physicists should care about as physicists, not as doing something else, right? And they're the kinds of questions philosophers care about just because that's the kind of questions we usually care about. What's going on at the bottom of all this?
You spoke about you covered a lot about how mathematical functions are a representation of a physical conjugate, physical correlate. I want to bring in Bertrand Russell. He had once said that reflection on philosophical problems has convinced me that a much larger number than I used to think, or than is generally thought, are connected with the principles of symbolism. That is to say, with the relation between what means and what is meant. In dealing with highly abstract matters, it is much easier to grasp the symbols, usually words, than it is to grasp what they stand for. The result of this is that almost all thinking that purports to be philosophical or logical consists in attributing to the world properties of language. Would you agree with Russell that it's inevitable that we have to use mathematical objects, structures, symbolism, language, formulas to try and capture these really big, difficult, abstract ideas, that there's no way around it, that if we have to make it comprehensible for humans, then we have to use one of these mediums. And in doing so, we are going to limit it, restrict it, cage it by the properties of that language. And our perception of the world will always be limited by the property of the language that we're using.
Well, of course, the way we think about the world is mediated by representations. Some of these are linguistic. Some of them are what we would call conceptual. Some of them might be visual.
Yeah.
It has to be. I mean, we think with representations about the world, and most of the world isn't itself representations, right? Some little bit of it. I mean, you've got some representations on your page there, but most of the world, the table is not a representation of anything. But of course, we think in terms of representations, and again, think of those as representational tools. And then you have to ask. It's good advice to reflect on your tools. As you know, there's this. I'm sure you know the phrase: "If all you have is a hammer, everything looks like a nail."
Yeah.
Right? If I'm only used to using these tools, I'm going to try to use them for every task there is. And maybe there's a better tool that could be invented that does the job more efficiently, that fits the problem better. And you're going to miss that if you don't reflect on what you're doing. So that's absolutely true. Ironically, what happened is in philosophy, as Russell was talking about, there was a lot of attention paid to natural language. And in doing that, because the structure of natural language is words that are laid out in syntactic order, that led to the structure of first order predicate calculus or logic, right? Standard logic. And ultimately that got understood in terms of set theory. I mean, we could go into this, but it would take a little while. But the idea is that what they weren't looking at was mathematics. They were looking at things like the cat is on the mat, where you have the sequence of words, the cat is on the mat, and you're trying to then represent that in some way and then say, what are the truth conditions for that? Natural language isn't the way physics is done. At a detailed level, you've got to write down differential equations and things like that. And those are the things doing the heavy lifting in the representation. So you should be thinking about mathematical structures and how they could correspond to physical structures. But philosophy, when it took what's called the linguistic turn, and focused itself pretty directly on these questions of how does language work, it tended not to be looking at all at mathematics. It was just looking at natural language. And Russell's certainly right. There are a lot of the grammar of your natural language you can incorrectly project into the world. And you make mistakes that way because you're not being self-conscious and self-reflective about the tools you're using.
And we just spoke about how mathematical objects also can be limiting.
Yeah.
So is there ever a world where we will not be bound by these limitations? Like, is there a way to actually start grasping these abstract ideas and try to eliminate the middleman, which is the property of the language that's limiting it?
Well, we can't eliminate the middleman in the sense that we're going to have to use some kind of mental representation.
Yeah.
Right. I mean, we can't just
grasp it.
just grab onto the world without the use of any concept.
Wishful thinking.
Yeah. Now, the question of whether, and mathematical physics largely uses mathematical objects as means of representation. Now, someone might say, but isn't that limiting? Maybe the world can't be understood mathematically. At this point, I don't know any other alternative. I mean, look, maybe somebody can come up with an alternative that we would say that's not math, but gee, here's how it works. Yeah. I can't think of any other alternative. And furthermore, there's the abstract mathematical universe is infinite, certainly. And there are lots of mathematical structures that have been discovered and developed in the last 100 years for use in physics. There are lots out there that have not yet been discovered or investigated. If you were to tell me, gosh, I don't think any piece of mathematics is going to be adequate for doing physics. Ultimately, for doing physics, I'd say, well, it's done really well so far.
Yeah.
Right? I mean, the way we got these predictions about the anomalous magnetic moment of the electron or whatever is by using mathematical representations. I don't see any evidence. I don't know what it could look like to suggest that no piece of mathematics is up to this job. Now, I'm a philosopher, so we're always used to these kind of weird skeptical scenarios. But this is the kind of thing where the only answer to the skepticism is say, well, the only way to find out is to keep trying.
Yeah.
And I don't see anything going on in the physical world where the conclusion is mathematics is not in principle up to providing us the means to account for this. There's a very bad argument that Roger Penrose gave that goes through Gödel's incompleteness theorem that's supposed to have this consequence, but that's a bad argument. And I think everybody, any logician understands it's a bad argument. I don't know of any good arguments that would suggest that you should be looking anywhere other than mathematics. And if someone said you should, I have no idea where they're supposed to be looking. You're not going to be looking at everyday natural language.
Very interesting. Let's pivot a bit and now start talking about some of the heavy stuff. So let's pivot into the work John Bell has done. But before we talk about Bell's theorem, I would love it if you can define some terms that we'll be using. So what is realism? What is locality? How does that fit into quantum physics or the quantum predictive recipe, as you've called it?
Okay, so let me just say about the first one, there's a term realism or scientific realism. It has a perfectly good meaning in philosophy. I don't think it's relevant to this discussion at all. I think that one of the great distractors that has kept people from understanding what Bell did is somebody at some point, and recently there was a paper about the history of this. I can't remember the details. Somebody started sneaking the word realism or realist into accounts of Bell's theorem. Bell didn't use it, and it shouldn't be there. So they'll say, oh, Bell showed that a certain sort of realist theory can't account for this. And then you'd say, well, what is a realist physical theory? And the answer is that's not even grammatical. It doesn't make any sense. In philosophy, scientific realism is a thesis about, do we ever have enough evidence to warrant belief in a theoretical postulate, in something you can't, in some sense, directly observe? I mean, if you go back to Descartes, he's asking, do we ever have enough evidence to even believe in things we think we can observe, like tables and chairs, right? Maybe I'm asleep. Maybe there's an evil demon, blah, blah, blah. But if you go to that level of skepticism, why are you talking about physics, right? If you're not really sure that there are such things as laboratories or stars or, okay, you can ask that question, but this is so distant from any physical considerations that it's not quite clear why you'd be bringing physics into it. Somehow at the beginning of the 20th century, the logical positivists sort of said, well, we're okay with things like tables and chairs and cats, but we're worried about atoms and electrons and things like that. Yeah. So then there was this distinction between observable and theoretical entities. And then scientific realism is the thesis, which I think is absolutely true, that at least sometimes we can have evidence that makes it rational to believe in certain things you can't directly observe. As I said, I believe in DNA. I believe there's such a thing as DNA. It has a double helix form. It has these 4 base pairs, and the base pairs connect in certain ways. And that explains a whole bunch about cellular, how cells work. And none of that is directly observable. So, but what does that have to do with anything? It has nothing to do with anything, because what Bell is about is about what in principle can a certain type of theory explain. Not what is the evidence that we could have for that theory, or should we even believe such a theory? But in principle, if I take any physical theory and put a certain restraint on it, which is a locality constraint, so sometimes called Bell locality or relativistic causality, so an abstractly definable constraint of what the physics is allowed to do, I don't care what the physics is, there are certain things it could not predict, and therefore certain things it could not explain. And I said all that without mentioning the word realist. So the problem is people first they sneak the word realist in, and then they say, well, I don't like Bell's result, so I'm just going to deny realism. And then his result goes away, right? His theorem doesn't apply because I don't believe in a realist physics. And you go, what are you even talking about? Any physics is making postulates about how the world is. If you're not doing that, you're not doing physics. You're doing something else. I don't know what you're doing, but physics is about hypotheses about the structure of the physical world. That's the only sense of realism, right? It's an attempt to describe the real physical world. Real is a funny word. I mean, I'll just say this final thing people can think about. Real is a funny word because it doesn't actually mean anything. So I say, I have a dog. Good. I have a real dog. Yeah. I have a real actual dog. Yeah. I have a real actual dog who actually exists. Yeah. I just said the same thing 5 different ways, right? Adding real, if I say I have a dog, but it's not a real dog, then the answer is then you don't have a dog, right? You have, I don't know, a stuffed animal that looks like a dog, or you have but you don't actually have a dog. Real people put a big, capital R real or capital T true, same thing, right? I have a dog, good. The statement I have a dog is true. Yeah. Yeah, I've just said the same thing in different, they're equivalent in a certain way. Saying that it's true is just the same thing as saying it. And capitalizing the T in true is doing nothing but changing a typeface and trying to impress people with it, right? There's no difference between little t and big T. True is true. So sometimes people will sneak these words in that don't belong there and then think they can escape from the results by pointing at the thing they snuck in, saying, I'm going to reject that. And this is just completely illegitimate, right? Completely illegitimate.
So we've discarded realism. What is locality?
So locality is the first idea is kind of Einstein's idea when he says he didn't believe in spooky action at a distance. Mm-hmm. So at the first pass, you say locality is saying that something that happens here, of course, you need locations for locality. The locations are in space or in space-time. So I have some object here. And the basic idea of locality is that the only way, first of all, this object can only immediately affect things that are very near it in space, right next to it. It can't immediately affect things that are very far away. So it's perfectly comprehensible how this can make that thing move because it banged into it, right? This is kind of the mechanical philosophy. The only way one thing can affect another is by literally hitting it. Yeah. And that means they have to be next to each other in space. Mm-hmm. If you were to say, if I were a magician, I can't do this, and I could move this, and all of a sudden that moved, you'd go, oh, that's magic. Now, there are lots of things that happen that kind of look like magic. I remember the first time I saw a remote control, I thought it looked like magic. I'm holding this little box and pressing, and then the TV is changing. And I grew up where you had to go and change the TV. But then you stop and you say, well, I understand. Again, there's a beam of infrared light that's coming out of this box that's going to the TV. And then that's also local because it's a chain of local events. The basic idea of relativistic locality or Bell locality is that if you think about it that way, if you think in order for me to press the button on this box, for that to have an effect on something way over there, something has to go from here to there. And now you add this restraint. It can't go faster than light. That's why it's relativistic causality. That the speed of light provides a limit to where my pressing this button can have effects in the future. They have to lie, as we say, in or on the future light cone. Otherwise, the effects would be superluminal. That's a clear constraint. And what Bell proved is that if you just put that constraint on your theory, just locality, local causality or relativistic causality, the theory cannot explain certain phenomena. And those happen to be phenomena that quantum mechanics predicts, and much more importantly, they're phenomena that actually occur in the world. The world does not obey relativistic causality. So that's locality. But the basic idea, I mean, Einstein's basic idea of spooky action at a distance is okay. You take Alice and Bob and you put them in two labs and you put them 100 million miles away. And you say, well, nothing that happens in Alice's lab can really have an effect or make a difference to what happens in Bob's lab.
Yeah.
You can think of that as locality. And it's commonsensical. And the thing that Einstein objected to about quantum theory from the beginning was, if you tried to take it seriously, it would be non-local. He saw that immediately, not to do with Bell, but he saw immediately that the way people were using quantum mechanics involved this non-locality, because it came up immediately in what's called the collapse or reduction of the wave function, because the wave function for a single particle is sort of spread out all over everywhere. And it evolves usually by a nice local, for a single particle, it would be a nice local equation. You can understand it that way. But then sometimes it was supposed to do this other thing, collapse or reduce. And that happened globally and instantaneously. And for Einstein, that was spooky action at a distance. So you're saying an event happening here is affecting this wave function everywhere instantaneously. And he could never accept that. And he couldn't see any reason to believe it. I mean, the main thing for him was, he said, why are you saying this? The phenomena don't require it. And the phenomena were simple things like, you have a radioactive atom and you have a whole detector around it. And eventually a dot appears somewhere on that detector. You can't predict exactly where. Now, in the standard account, the wave function is, as it were, leaking out in a spherically symmetric way. There's bits of the wave function, if you will, all the time leaking out in all directions. And then at some point, for reasons they say cannot be explained, a spot appears here.
Yeah. And
that's weird enough. But what's even weirder is the moment that spot appears, there is no possibility that a spot will appear over here, right? A second ago, it could have. But the appearance of this spot is accompanied with the collapse of the wave function, which kills off any possibility of a spot anywhere else. And Einstein said, that's just silly. I mean, all that's happening is some particles being shot out in some random direction, right? We can't predict it. And of course, if it shows up here, it's not going to show up there. So what Einstein thought was actually the same thing the cubeists thought. They say, look, this isn't a physical effect, this collapse. It's just an epistemic thing. It's updating on new information. And of course, when I update on new information, I can learn new things about what's going on far away. Not because there's any physical change far away, but just my knowledge is changing. That's not spooky at all. And in a way, the motivation for cubism was to say, we don't like spooky action at a distance either, so we're going to treat the wave function, as I say, it's if the wave function is attached to my head and not to the object, then the collapses become trivial. They're just what we call Bayesian updating. You get some new information, you change your set of beliefs about the world. That's trivial, nothing spooky about it. That's what Einstein wanted to understand the collapses to be. But again, you can't relegate the wave function merely to being this set of beliefs because of things like two-slit interference, where the wave function is going through both slits, and it's important it goes through both slits and they interfere. And that's not about my knowledge. That's about something going on, in the lab.
Where do hidden variables fit in this?
Well, hidden variables, again, I always say, Bell said nicely, he said the term hidden variables, he called it a piece of historical silliness. And he's absolutely right. Because the word hidden, because they're not hidden. I mean, in the theories that employ them, they're not at all hidden. They're the opposite of hidden. They're what's manifest. And it's the quantum state that's represented by the wave function. That's hidden. That's hard to see. Where this comes in is exactly where I mentioned before. On any reasonable theory, the quantum wave function has to represent something physically real. Let's just call that object the quantum state. That's my terminology, just to separate the mathematical representation from the object represented, right? The representation is the wave function. It's a function. Functions are mathematical things. It's a complex function. I can talk about the math of it. It represents this thing, physical thing, call it the quantum state. Question, all right, if you believe in that, is the quantum state all there is? So you think that's part of reality. Is there any more to physical reality? If you say no, there's more than that, then you have additional variables, right? The quantum state is one variable. It's one thing you have to specify the physical situation. And you say there are other variables, like what? Well, you might say in addition to the quantum state, this is the pilot wave picture, there are particles. Particles move around. So there are these variables. You have to tell me where they are, for example, to specify the full situation. So that's all this talk of hidden variables is about, is they should be, first of all, be called additional variables, not hidden, because they're not hidden. And you, of course, you'd be very puzzled. Why would I postulate something hidden to do physics? Because if it's hidden, what difference does it make? I mean, who cares what invisible things are doing? What's their role? But they're not hidden. They're actually the things in that theory that make up the things we immediately see. Tables and chairs and pieces of Lego and so on are made of particles. Why does this piece of Lego have this shape? Because they're a bunch of particles. They have this shape. Straightforward. The main problem, and this is, again, another thing, I'm just keep bringing up Bell. Bell writes a very nice paper called The Theory of Local Beables. And Bell invented this term beable, and he invented it to contrast with the standard physics term observable. So physicists all the time will talk about what are the observables of your theory. And observables, obviously the word has something to do with observation. And Bell said, yeah, but anything observable must be built out of something that's just there, that just is. Mm-hmm. And so beable, right? What is there? What just exists independently of being observed? And he said any theory should have local beable. So this comes back to the locality. It should have something physical going on in little parts of space, right? This is a local object. I'm holding it in my hand. It's here. It's not, it's not out the window. It's not on the other side. It's here. The wave function isn't. The wave function that can't even be defined on physical space once you have more than one particle. So you can't think of the wave function or the quantum state as a local beable. Everybody should agree about that. And Bell said, but you better have some. The people who don't want anything other than the quantum state, this is a big problem for them because they can't deny that we talk about local things in space and essentially talk about them in describing physical experiments. So you need that language. The easy way to understand that language is to say, well, there is more to the world than the quantum state. There's something local. Maybe a particle, maybe a field, maybe there are these things called flashes. Okay, there are different proposals for what these local things are. But it's from the local things that I build up local objects of everyday life. So that seems to me obviously the right way to go. It seemed to Bell obviously the right way to go, that any decent physical theory should have some local beables. If it has a quantum state, that's not a local beable. So it's going to have some local beables and some non-local beables. And why do I have both of these? Well, why do I introduce, now you say, why do I introduce the quantum state? Why do I introduce this weird non-local thing? And the answer is because of the role it plays in the theory of influencing the behavior of the local things. It's the local things we can see. There's a good analogy here that's often used to electromagnetic theory. As I said, Maxwell, Faraday, and so on, these people introduced the idea of a field, an electric field. This was new. Democritus just has atoms in the void, no fields. So this was a novel proposal. And you can't directly see an electric field. You can't directly see a magnetic field. Why do you think it's there at all? Why do you introduce it into your physics? Well, you can see things like magnetic needles moving, right? That's matter. That's not field. That's the matter part. And you notice, gosh, these particular ones, they jump or they always point this way. they behave in certain visible ways. I need to explain that. And so you postulate a not immediately observable object in the service of explaining the behavior of the visible objects. So everything we can think we can directly observe is local, right? I go into the lab and I report what's going on in the lab, and everything I report is stuff in the lab. This dial was set this way and this spot appeared here. That's all local stuff. That gives me the data that physics has to explain. I get something out of CERN, and it's this thing with all these spirals and these pictures. These are all local things, and then I postulate what I need to account for them, and that can involve local things I can't directly observe, like fields, and it can involve, weirdly enough, having to postulate non-local things like quantum states. That's the real novelty of quantum theory, is that it postulates at a fundamental level something that isn't a local object.
Well, we've set the context, and you have brought John Bell multiple times, but I do want to formally introduce him. And this might be a bit redundant because we have spoken about him, but who was John Bell? What was the Bell experiment, Bell's theorem, Bell's inequality? And I think it's worth stating again, what were the implications that it had on quantum mechanics?
Right. So Bell was a physicist. He was Irish. He grew up in, I guess, kind of lower class circumstances where I think it was unusual to even go to college. He became a physicist, got a very good education. And the main thing about him, though, was not his education. Of course, lots of people got good educations, but just, again, his insistence on trying to understand things. Of not being satisfied with just being told this is how it is and don't ask. And so Bell had the same experience that everyone does when he was first taught quantum mechanics, is he didn't understand what was going on. Which isn't to say he didn't understand the mathematics and he couldn't do the problem sets and do well in it. That's a different matter. I call it the quantum recipe. There's an algorithm for using this to make predictions. Anybody with a little bit of mathematical facility can do that. But if you ask, but what's going on in the physical world? What are you telling me about the physical world with this? As I say, a standard quantum text will not even attempt to answer that question, and a standard physics teacher will try to dissuade you from asking it. And Bell thought the way anybody would normally think, as I say. So go back to the example that Einstein worried about. I have a piece of, and this will connect up to Schrodinger. I have a radioactive atom sitting in the center of this spherical detector. Quantum mechanically, what's happening, well, let's not worry about quantum mechanics. If I do this many times, what do I find? I find that, if I wait, eventually a spot appears. It will appear in different locations and not preferentially anywhere on the sphere, and it'll appear at different times, right? So sometimes I have to wait a long time, sometimes a short time. I have statistics about that, about how often these spots appear, but they appear spatially in no preferred direction. Quantum mechanics says, you've got this wave function, this quantum state for your radioactive atom. And all the time, it's as it were leaking out in a perfectly spherical, symmetric way in all directions. It's kind of just leaking out. And if you want to know the likelihood at any given moment that a spot will appear somewhere on this sphere, you take the amount of quantum state there is there at that moment and square it, and you get a number, and that number will say, this is how likely.
Yeah.
Okay. That's how it works.
Mm-hmm.
And then you say, but what's going on? But wait, why does the spot, why does the spot appear here? Now, the natural thought is, there's some interior piece, an alpha particle, or, some neutrons, electrons, whatever, in this, say, uranium atom. that's kicking around in there. I mean, now very Democritean picture, somehow vibrating or kicking around or moving around. And eventually it kind of works its way out and shoots off in some direction. Now, maybe it could come out in all kinds of different directions, and maybe it could come out in different times depending upon how it bounces around. But that's really what's going on, and that gives rise to this distribution of spots, both over space and over time. But that would be a hidden variables theory, because it's postulating there's something that's not described by the quantum state, namely the actual location and motion of this little thing that shoots out. So anybody who looks at this is going to say, well, tell me about that. And this is where Bohr will say, no, there's no story like that. You can't think that way. And Bell's immediate result, as any right thinking person would be, is, well, why can't I think that way? It seems like a good way to think. It seems like the obvious explanation. And then he says he was told, well, von Neumann, the mathematician von Neumann, has proven that no such hidden variables theory can work. That is, no hidden variables theory can reproduce the predictions of quantum theory. It's impossible. It's mathematically impossible. And Bell said, well, he was shocked, right? He was surprised. And he just put it out of his mind. Why? Well, because von Neumann's book had not been translated from German into English, and he didn't read German. So there's nothing else he could do. And he was told by this expert, right, his professor, von Neumann, person who ought to know, von Neumann has told, has a proof. So stop trying to think that way, because he's proven it can't be done. And then in 1952, David Bohm publishes a paper in Physics Journal called Hidden Quantum Mechanics in Terms of Hidden Variables, part 1 and part 2. And it is exactly what it says it is. It's an account of quantum mechanical phenomena that does postulate additional variables. He called them hidden, but anyway, additional variables. And Bell read that, and he read it carefully, and he said, yeah, this works. I mean, what Bohm has written here does in fact reproduce all of those predictions. It would predict that you would get these spots with this distribution. And it's done in terms of these additional variables. Hey, what's going on, right? My professor told me that von Neumann had proven that you can't do this. And I have in front of me a flat counterexample. Here it is done. And at that point, he could get von Neumann, and he gets the book, he looks at it, and he immediately spots an assumption. It's not that von Neumann made a mathematical error, but he makes an assumption in his proof. And he said, Bell later says, the assumption was foolish. It was foolish is the word he used. Not a reasonable physical assumption. There's another interesting story, which is that somebody goes, I think in the 40s, I'm not sure, to Einstein when he's in Princeton. And Einstein's been thinking also in terms of these additional variables all this time. And the interviewer, I can't remember who it was, says, yeah, but what about von Neumann? And tells a story that Einstein goes to his bookshelf, pulls von Neumann's book off the shelf, opens it to a page, points to something and says, there's no reason to believe this. And it's the same thing that Bell, as soon as you're thinking this way, as soon as, you cast a critical eye on what von Neumann did, it's not hard to see that there's an assumption which has no real justification. And many people saw that, but it was suppressed. It was much easier to tell your students, von Neumann settled this, stop trying to think this way.
What was the assumption? I'm sorry.
So the technical assumption, the mathematical assumption, I'll try to describe it. In quantum theory, as I say, they talk about observables. That's the thing Bell didn't like. He said, well, talk about beables, talk about what there is, not what you can observe. But these observables in quantum theory are associated mathematically with things called Hermitian operators. So these are just well-defined pieces of mathematics. So you say, position, that's an observable. What's the operator? Here it is. Momentum, that's an observable. What's the operator? Here it is. These operators have mathematical relations between them. So one can be the sum or the difference of others. They're well-defined mathematical relations between the operators. Von Neumann's assumption was that if you postulated these additional variables that were accounting for the results of, say, a position experiment or momentum experiment, right? Why did the spot form exactly here? So I postulate some actual object that was there. He assumed in his proof that these additional variables, their values would have to be mathematically related to each other in exactly the same way as these operators are mathematically related to each other. And there's no reason to assume that. I mean, Bohm didn't assume it. And Bell, on thinking about it, said, why would you think that? Why would you put that constraint on an additional variables theory, a hidden variables theory? It's not a reason. Physically, it's not a reasonable constraint. And Bell even gives a little short argument that says it's immediately obvious if you put that constraint on, of course it can't be done. You don't even have to go through much thought just to explain things about angular momentum. So he said, yeah, that's foolish. Yes, I understand I can't build a theory with that particular mathematical constraint on it, but I see no reason to put that constraint on it. And if you take that off, you can do it. And here, Bohm has done it. And long before Bohm, really, Louis de Broglie did it. I mean, back in the 20s. So it's not even very hard to find a theory that works that way. But people convinced themselves because they didn't, again, the only explanation for this in my mind was that a bunch of physicists were very, very psychologically motivated for there not to be such a theory. They didn't want there to be such a theory. And von Neumann had given them a kind of straw to grab onto and say, look, it can't be done. You're just wasting your time. Get with the program, right?
Yeah. Let's restate then. So we spoke about John Bell, but what was Bell's inequality? And what implications did it have for quantum non-locality?
Good. So Bell says, suppose I have a relativistically local theory. That's well defined. It doesn't even have to be quantum, it doesn't have to have anything to do with quantum mechanics, whatever theory you like, but it does have this constraint. Intuitively, I separate Alice and Bob. Whatever happens in Alice's lab can't have any direct effect on what happens in Bob's lab if I put them far enough apart. And if I do the experiments in such a way that even light couldn't get from one to the other to have an effect. So that's a good constraint. And he says, well, in that case, there's just certain things that couldn't happen. There are certain, in particular, correlations between the outcomes that Alice sees and the outcome that Bob sees that could not be predicted and therefore could not be explained by any local theory. And there's the mathematics of showing this in detail, which isn't that hard. Maybe there's an analogy I can give, which is not exact. This is not exactly what's going on, but just to give people the sense of, you say, well, what do you mean it's impossible? I mean, suppose again, I've got these Legos. Okay, suppose I say, all right, there are 3 Legos. And I'm going to have them hidden. And you're allowed, however you want, to indicate any 2 that you're going to look at. Okay? And it's a completely unconstrained choice, right? You can decide which 2 you indicate however you like. But here's an interesting fact. And there are only 2 colors that ever show up. There's this light green and this dark green. But here's an interesting fact. All the time, whenever you indicate any 2, whichever 2 they are, and I reveal them, they'll be of opposite colors. Okay? And you stop them and you say, wait, how can that be? I mean, there's a trick, because if they're all 3 the same color underneath here, then whichever 2 I pick will be the same color. And if 2 are the same and the other's different, still, I could pick the 2 that are the same. How could it be that every time they're different, right? And then I do it. Well, that didn't work. Okay, I do it this way. Look, they're different. But, you do this over and over again, and you keep picking, and every time, and you're going to say, wait, there's some sleight of hand going on here, right? Somehow, you can't just be revealing to me the colors they already have. You can't prearrange them to have colors in such a way that every pair, there are only two colors, but every pair has a different color. It can't be done. So there must be some way in which your choice of which two to look at, and this is a case where, for whatever reason, you can never look at the third one, your choice of which two to look at is actually going to have an effect on which colors they are. So maybe I'm a magician, and after you've chosen, I'm good at sleight of hand, and I can switch these things around. But I have to do that. I can't just literally put them under my hands in a way that will always work.
Yeah.
So that's the kind of thing. I mean, it's not exactly that, but that gives you a flavor for the kind of way you could say, in that case, I say, look, if your choice of which two to look at has no effect at all on the colors themselves, then that's a behavior you just can't get. Bell's is like that. Bell says if Alice's choice of what experiment to do has no influence at all on what happens in Bob's lab, and Bob's choice of what experiment to do has no influence at all on Alice's lab, then there are constraints on the kinds of correlations they could see. So that arises for any causally local theory. Now, the two interesting facts are, first of all, that quantum theory predicts violations of those constraints. And then again, the important thing is that you go into the lab and you check, and they are violated. So that tells you no locally causal theory can work. So that tells you there's something kind of causal influence that's faster than light.
Yeah.
That's the short story. Now, it's not that hard to give you an exact. The story here is when Bell does his original work, he's looking at pairs of particles in these special so-called entangled states, and he gives you an argument in this form. Later on, Greenberger, Horn, and Zeilinger come up with a slightly different example that involves three particles. And now I've got Alice and Bob and Charlie all in their labs. And then you can prove in just the same way that I just did, you can't prearrange. I'm going to create a triple of particles, send one to Alice, one to Bob, one to Charlie. You can't prearrange them to have properties that are merely revealed by these experiments in a way that would give you the right statistics. Can't be done. That's what he proved. And you can't get around it. And you can't get around it by saying, oh, I don't want to be a realist. I say, well, who cares? I don't care whether you're a realist or not, right? This is just mathematical. This really is a mathematical proof that a certain kind of thing can't be done.
Firstly, not many people even know of John Bell. And then not many people even know of Bell's theorem. Whereas a lot of people know of Bohr, they know of the Copenhagen interpretation. Why do you think that is? Like, if we had to dissect this as a case study as well, at what point did this interpretation become more prevalent in the industry, so much so that people haven't even heard of John Bell, and that type of thinking has just been suppressed?
Well, it's not, I mean, you're right, but if to understand the suppression, you can go back before Bell. So you think, here are some people have heard of: Albert Einstein, Erwin Schrödinger,
Yeah.
Right? I mean, Schrödinger's equation is at the center of quantum theory. Einstein's paper in 1905 on the photoelectric effect was really the beginning of quantum theory, I would say, rather than Planck's earlier work. So these were people who were well known, were very intimately involved in the creation of quantum theory. Yeah. Both of them complained as loudly as they could about Bohr and Copenhagen, right? And rejected it and said it was nonsense and said it was incoherent and said you can't make sense of it. And they were kind of shunted aside. So you can say, well, all right, Bell was some unknown guy from Ireland who was working at CERN. Yeah. It's maybe, and it would, if not for a series of almost accidents, he could have published his paper and almost been, it just died. It was published in the first volume of a brand new physics journal that went out of business within a few years. That paper could have sat on dusty shelves and not been noticed by anybody. It was only by great luck, in a way, it got into the hands of Abner Shimoni, who appreciated it, and Shimoni's student was John Clauser, who was looking for an experiment to do. And I mean, there are various things that happened. They might not have happened. It's not clear. But before you ask why isn't it people haven't heard of Bell, first ask, how could they have sidelined Einstein so effectively? Albert Einstein, when he's complaining, spooky action at a distance, right? God plays dice. I mean, all these very loud complaints. Quantum theory is wrong. It's all nonsense. And how did they do it? They said, Einstein, he got old fuddy-duddy. Who cares about Einstein? Don't listen to him. It is a sociological fact that Bohr was certainly a much better organizer than Einstein. Einstein, in his later life, was working by himself. His only collaborators, Podolsky and Rosen in this paper in 1935. Schrödinger, when he was raising his complaints, working by himself. So the opposition to Copenhagen was scattered and was not acting as a organized corporate body. Bohr was good at organizing. And so he had, he got Heisenberg. They didn't really agree, but they nonetheless presented a kind of unified front. And this guy Rosenfeld, and they could be pretty ruthless in some ways in enforcing the Copenhagen orthodoxy. So I think that's the real story. And then Bell is just this guy who's not at the center of the theoretical community at all. And he's a very practical guy working at CERN. And he's just a good thinker. And he figures this out and publishes it. But he was nice enough. I think it was a friend of his who was starting this brand new physics journal, volume 1. He said, here's a paper I just wrote. Not even trying to get it published in the established central physics journals. Just a nice guy, right? And he had no means to enforce any of this. What happened was enough people ended up hearing about it and seeing the point to see this is very important. But they were kind of people on the fringes. Or from the beginning, there were people on the fringes who took this up, who understood it. I learned about a lot of this. I learned about this in two places. I learned about it in a 1979 Scientific American article by Bernard Despeignat, and then a book called Quantum Reality by Nick Herbert, which came out a little bit later. But these were not the big names in physics, right? These were always people who were in a way on the fringe.
It's so surprising to me because for me, science is always like the bastion of empiricism, evidence, celebrating curiosity. And even if there's someone on the fringe who's out of the group, but who has an idea and it's about exploring knowledge, then that should be celebrated. In fact, that's the virtue that science rose up on to challenge religion. Right. But the more I learn about string theory, multiverses, the Copenhagen interpretation of quantum mechanics, the structure around peer review, it just feels to me that science has now reached that funny side of the life cycle where it's standing for everything that it rose up to fight against, where it's become all about ideologies and groupthink and cults, and anyone on the fringes who's actually challenging convention is just thrown off.
Yeah, I would have to say, it's not that it's become that way. In a way, it's always been like that. But you shouldn't sell short the fact that as it were, the little dissidents do eventually win out. There's a kind of standard example we use in philosophy of science a lot. In the medical tradition, people ascribed ulcers to stress. This was just common, right? You got an ulcer, you're under stress, you take a break, try and relax, maybe do something for your stomach. Your stomach is producing too much acid. Why is it doing that? Well, because you're under stress, blah, blah, blah. Now, there were these researchers who just didn't accept it. They said, wait, no, maybe it's just much simpler, right? It's a bacterium. Maybe something got into your gut. Yeah. And this was, again, the mainstream medical establishment really resisted this. Why? Well, one reason is, as is pointed out, there's a wonderful quote from Tolstoy that Shelley Goldstein often uses. People don't like to admit they were wrong. just to boil it down to that. And Tolstoy says it in a very fancy way. If someone has built their life explaining something to other people, right? Like a professor standing up before your students and saying it's like this and this, you do not want to have to say at some point, I was wrong.
Yeah.
Right? I mean, there's also the psychological resistance to your admitting to yourself you were wrong. In the case of the ulcer, I can't remember the name. There's a researcher who's an Australian, and they decided, no, we think this is a bacterium. And the one guy was brave enough. He actually swallowed it and induced an ulcer in himself on a human subject. And it was himself, because he couldn't do any this to somebody else, to say, I'm going to show you that what causes ulcers is not stress. It's H. pylori. And he was right. Now, it has the two sides to it. It has the resistance. That resistance is intrinsic to any large-scale enterprise. It's intrinsic to human psychology, right? Not wanting to admit you're wrong, defending. We see that everywhere, right? You see it in politics. You see it everywhere. So you shouldn't be surprised. Scientists are human beings. They're subject to the same psychology as all human beings. You should be impressed that, unlike in some places like religion, the good guys win out in the end, even if they're small, even if they're little, even if there are only a few of them, that they can have the tools, the arguments, and the data, and enough people who listen, that eventually they win. I mean, physicists have been upset about people talking about pilot wave theory since it was produced. And you talk to some of these physicists and they're very frustrated, right? Why don't these people go away? Why won't these people go away? And the answer is because there are enough people who read it and with an open mind and see the point and say you shouldn't be dismissing it. And they keep at it. And eventually, it wins. I mean, I think you're right. I think what happened with string theory, I mean, there were reasons to be interested in string theory. It's not that string theory was just a fantasy.
Mm-hmm.
There were reasons to think it might be a promising way.
Yeah.
It went way overboard in terms of capturing the high energy physics community. I mean, when I was still at Rutgers, they hired what was called the string quartet. They hired 4 string theorists all together. That's more of an investment in string theory than was made in pilot wave theory over what's now a century, right? That one thing at that one university was putting more resources, more people together to try and work out that theory than have ever been put. Okay, they went way overboard. And then once the professors are doing that, then their graduate students are being taught that. And then, it takes on an inertia and it takes on a bureaucratic institutional life of its own. And it was very hard for people doing something else or thinking maybe there are other ways to do this to get traction and to get funding and so on. I mean, now that's not peculiar to physics. It is going to be the same in every academic discipline. You should just be aware of it, right? You shouldn't idealize. You should not over-idealize science, but you shouldn't under-idealize it either, because it's still much, much, much better than many other things where that's all it is, right? All it is this kind of stuff. But, at the bottom of physics, at the bottom of empirical science, there is data and there are some clear arguments, and eventually they can have effects.
So it's a waiting game.
Yeah. It's a waiting game. I mean, in the case of string theory, it was kind of having to wait long enough for results to come out of the Large Hadron Collider to make people say, wait, we're not seeing this stuff. Or, early on, the supersymmetry, again, you're too young for this. I was around when supersymmetry became popular and people said, oh, then the proton can in principle decay. And then they set up these huge spheres of perfectly clear water in mines and looked for Cherenkov radiation that would be the signature of proton decay. I mean, I was around when they said, oh yeah, we may have to wait a decade to get a signal, but eventually we'll see this and this will revolutionize physics, which it would. They just never saw it. And of course, the problem is if you saw it, it would be all headlines. as soon as they see it. But if you don't see it, there's never the headline, they still didn't see it, right? And so it just kind of quietly, all of these proton decay experiments fell out of people's minds, which means they didn't draw the natural consequences. Well, maybe there isn't supersymmetry. Maybe this can't happen, which is what we thought. And I think with the Large Hadron Collider, people were saying, oh, we're going to start to see some of these supersymmetric partners. They didn't show up. And so you had to wait that long, I think, for people to say string theory. I mean, there were, as you know, there were skeptics from the beginning, very strong skeptics, but they were mostly sidelined and ignored. They became kind of minority. But eventually the data caught up with them.
Okay. I'll wait a few lifetimes, a few generations. Looks can be deceiving. I might have been around for the superstring revolution. Who knows? I hope that changes. Before we start wrapping up, I also wanted to cover another big topic, which is time. Wilfrid Sellars had created a manifest image of the world in which he had divided the world into 4 dimensions, 3 of space, 1 of time, giving us the space-time continuum. In contrast, many people have misinterpreted one of Einstein's letters to one of his friends whose son had died recently, where Einstein had called time an illusion. And people have latched onto that idea. I have to ask you, time is such a mysterious concept. So let me start with the silliest question possible. What is time? And is it real or is it an illusion?
Okay, so let me just say, I don't think time is mysterious. I mean, at a certain level, time is the least mysterious concept.
Okay.
Why do people say it's a mystery? So let's just be clear about one thing. And this comes back to the very beginning. We're cycling back to the beginning of the whole discussion. There are objects that are composite or derivative, right? So this Lego piece obviously has lots of different parts, and it has the word Lego, written on all these things, and it has a certain size and so on. Mm-hmm. And in understanding it, part of understanding it is understanding the parts it's made out of and how they're put together, right? Ultimately, it's made of atoms that are put together in a certain way that, reflect and absorb different kinds of light. That explains the color. And those atoms are ultimately made of electrons and protons. Protons are made of quarks. Okay, so we can kind of, for most things in the world, the question, what is it? Part of it, at least, can be addressed by saying what it's made of. Okay, what are the pieces? What are the elements or ingredients that go into it, and how are they put together? So we're used to that kind of answer. But immediately you notice, if you think about it this way, but wait, when you get down to the bottom, when you get down to the fundamental are exactly the things that aren't made out of anything else. Okay? That's what makes them fundamental. They're not derivative. They're not composite. Well, obviously you can't answer the question, what is it, in the same way. That doesn't mean it's mysterious. It just means it's not composite. I mean, time, it seems to me, is not mysterious. It's mysterious. If you think, well, what is time made of? Yeah, I have no answer to that. I can't think of anything more fundamental than time from which I can derive time structure. But that doesn't make time really all that mysterious. I mean, nobody thinks it's particularly mysterious to say that it's now, 90 minutes or whatever later than it was when we started this discussion.
Sure.
And time was going forward, time was going from the past to the future the whole time. And, time is an absolutely everyday concept. Now you can ask detailed questions about the structure of time, about the temporal structure of the world. And there's a kind of common sense way of thinking about time, which Newton used, parts of it. So one thing that Newton said, and he says this very nicely in a paper called De Gravitatione, he's talking about time being made of these instants, moments of time, moments of duration. So, snap my fingers. That happened at some time. And Newton says, look, that instant of duration is the same in London and in Rome and on the stars and throughout the universe. Meaning, when I snap my fingers, that moment of time exists, and something was going on just then over in that the apartment way over there, and on Alpha Centauri, and off in that galaxy. right? It's a global, these instants of time are global. That's the way we intuitively think about time.
Yeah.
And these instants of time succeed each other. They go from the past to the future. We can measure, there's a measure of that duration in terms of seconds or minutes or hours. We make clocks to measure it, right? I mean, you've got time on your wrist. Time is it's not that. Now that's a theory of time structure. When relativity comes along, what happens in special and general relativity is you argue, no, that's not actually the correct account. Time has a different structure. The structure of time. It's not that time doesn't exist. It just has a different structure. The structure is given in special relativity and general relativity in a different way. And you get rid of these instantaneous moments, right? That's the main thing in relativity is you don't have this global instance of time. You get rid of that structure. And you do have a new structure called the light cone structure, which Newton didn't have. So you take away some of what Newton did have and you replace it with something that Newton didn't have. Yeah. And then in terms of this light cone structure, you can then, for example, formulate Bell's local causality condition. So that's a surprise. But on the other hand, okay, why should we think our everyday way of thinking about time is exactly accurate? Our everyday way of thinking about objects is that they're infinitely divisible. That's what Aristotle thought. Aristotle thought you take some water, you can cut it in half. And then you take that half, you can cut it in half. And you can do that forever, right? You can take an amount of water, you can cut it always into smaller and smaller bits. You might say, okay, maybe. Turns out that's not right. Once you get down to one H2O molecule, you can't cut it in half and still have water, right? That matter has an atomic structure. That's not every day, but it's not that hard to understand either, right? Aristotle might have been right. Maybe you could keep cutting it forever. These are just things where the only approach is to say, all right, let's try and think of different clear conceptions of what's going on, and then see, can we get some data or make some observations that seem to tell in favor of one of these rather than another. So I mean, I think people way over, when you say time is mysterious, I really don't know. I mean, maybe let me say one more thing. If you're a philosopher all the time, you start reading Descartes' Meditations. Meditation 1, he raises all these skeptical problems. How do I even know I'm sitting by the fire writing, right? Maybe it's all a dream.
Yep.
Maybe there's an evil demon or God is fooling me or whatever. Okay. So Descartes manages to question even the existence of spatial objects. He never questions time. Even in a dream, time is going on, right? Even dreams unfold in time. They have a beginning, a middle, and an end. Even if Descartes is dreaming that he's sitting by the fire writing and there's no pen and there's no hand, still, that dream is going on in time and it has a certain temporal structure. So even Descartes didn't question the existence of time. So when people say time is so mysterious, I don't know what they think is so mysterious about it. We need to think hard about the kind of detailed, precise structure it has. And there are different possibilities there. Newton postulated one, Einstein postulated another. I'm doing some work that's postulating yet another. But is it all that mysterious? It's not that mysterious if you think there's this fundamental succession, which is the nature of time.
What's your postulate, if you're ready to share?
Well, what I'm playing with are ideas that at base, both space and time are discrete, so kind of have an atomic structure. They're not continua, which is what all modern physics is based on, the idea that they're continua and you write down differential equations and so on. Maybe they're not. Maybe they're discrete. Well, the irony is, of course, whereas all the theories are written down in terms of continua, the calculations are all done on computers discretely. You put it on a lattice, right? You do a discrete calculation. Mm-hmm. And then there's some argument about why or why not the one should be a good approximation, or the conditions under which the one should give a good approximation to the other. My idea is that maybe at base it really is discrete, and the continuity is an illusion, as it were. Things at macroscopic scale, I mean, do they look continuous or not? Anyway, it's really fundamentally discrete. And the fundamental equations of physics should be written in terms of discrete quantities and discrete structures. That would immediately solve some problems, like there are these singularities and equations of standard physics that blow up, that go to infinity, and everybody understands that's a problem. And if you do things in a certain discrete way, you can immediately say it can't happen because you're just adding and subtracting a finite number of finite quantities at every step, so it can't blow up.
So it's possible to break time down into discrete fundamental units.
Sure, it's
like
possible. Yeah, everybody. I mean, even Zeno came up with these paradoxes of motion, and he had two sets of paradoxes. He said, well, if time is continuous, here's a paradox, like Achilles and the tortoise. And if time is discrete, here's a different paradox. The stadium paradox. I mean, you could go into details, but even in antiquity, it's not that hard to say, look, what do we know about time at the finest scales? Maybe it's continuous, maybe it's discrete, just the same as matter. Maybe it's continuous like Aristotle thought, you can always subdivide it, or maybe it's discrete like Democritus thought, you get down to an atom you can't divide. So it's not a surprise to say these are both possibilities. I think the discrete possibility has been understudied, that so much physics since Newton has been developed, and when Newton and Leibniz developed the calculus and so on, so much of it has been developed. Why? Because it was set in Euclidean space, and Euclidean space is continuous. And they assumed time was continuous. Maybe they're not. I think it deserves some consideration, because just saying that doesn't get you to a theory. There are many, many, many different ways of trying to implement the idea that space and time are discrete. I'm just working on one of them.
I want to tie this together with many points that you brought up. So you spoke about the direction of time. Clearly, we started at some point. It's been 90 minutes later.
Yeah.
So that's clear. I don't know if it's indisputable. Earlier we spoke about locality, speed of light.
Yes.
And we spoke about violating there's something faster than the speed of light. So I want to bring in direction, I want to bring in speed of light, and ask you the classic question: what happens when we travel faster than the speed of light? Is it possible to reverse the direction of time?
No. The obvious way to implement non-locality, which is really causal non-locality. I mean, the locality that Bell postulates is that all the causes of an event lie in or on its past light cone. Yeah. What the violations of Bell's inequality indicate is that no, there have to be at least some causes that, as it were, go outside the light cone. The easiest way to implement that idea, obviously easiest, most straightforward, unproblematic, is to go back to this standard Newtonian idea that there are these instants, right? That there's a foliation. You can take space-time and cut it into these successive slices. So you can picture it in your head. I've got a light cone from this point, which kind of goes back like this. But now I put a slice through that point that goes like that. And I say, okay, it can't be that all the causes lie back here, but it could be that all the causes are earlier, that you can still maintain that causes always precede their effects. Some of them go faster than light, but they always precede their effects in terms of this slicing. That's the easy way to do this mathematically, the easy way to do it conceptually. And if you do that, the answer is nothing goes backward in time. There's no such, I don't even know what going backward in time means, because you have to stop and say, what do you mean going? The term going implicitly assumes a direction of time, right?
Yeah.
Is this rock going from the Earth or to Mars, or from Mars to the Earth? Well, it depends on which way time is going. Okay. So to say something's going backward in time on the face of it just looks self-contradictory.
Right.
And so if you implement the non-locality the way I just indicated, which is not hard to understand, it's the way Newton thought about things, the way everybody thinks about things. Nothing can go backward in time. Causes can't precede their effects. There's no backward causation. But the light cone structure isn't a constraint, the constraint that Einstein thought it was on causation. So this is, maybe it's wrong, but man, it's easy to understand. I mean, it's not like I'm postulating something here that is just really, you have to take advanced, calculus or whatever. No, I mean, it's just this picture of time that, time involves an asymmetric relation of before and after, and it's transitive. So if this is before that and that's before this, then this is before that, and it just goes on, and there's this direction from past to future. And now you actually go back to what you're doing is taking away some of the mystery of relativity. Relativity told you what should strike everybody as a funny thing. So if I have this light cone structure, I can have two events that, as we say, are at space-like separation. Neither lies in the other's light cone. According to relativity, if you ask, but which of those happened first? The answer is there's no good answer to that. It's not well defined. The structure doesn't give me precedence, temporal precedence here. Mm-hmm. Your everyday thought is, well, wait, one of them must happen first, right? One of them must happen before the other, or maybe they happened at exactly the same time, but that's very unlikely. And all I'm saying is, go back to that picture. That's not a hard picture to understand. That's an easy picture to understand. That's the one you started with. And it turns out it looks like we need it because of these reasons Bell discovered. Now, as I like to say, I'm in a way criticizing Einstein and saying that relativity is misleading us about the structure of space and time. I'm not criticizing him personally because he didn't know about Bell. He didn't know about these experiments. He didn't know about any of this stuff. He was trying to recover Maxwellian electrodynamics and something like Newtonian gravitational theory, and those are local theories, and they can't violate Bell's inequality. And what he did in special and general relativity were perfectly adequate for the tasks he set himself. But he didn't know about Bell, right? He didn't live long enough. I like to think that if he had lived long enough, he would have seen the point. And he would have praised Bell and admitted his error. I mean, I like to think Einstein would have said, I was wrong. Maybe I'm being too optimistic, but my readings of him suggest to me that he was a man of great integrity in that sense, and certainly a clear thinker. He would have appreciated what Bell did. And I like to think he would have just admitted he was wrong.
Who knows? I can't say time will tell in this case. Ironically, we are running out of time as well. So before we move to our closing questions, I would love it if you can interpret what masterpiece you've been building with the Lego.
Well, I have not been building a masterpiece. I thought we would get into details about Bell's inequality and tests of it. So I was trying to make a Stern-Gerlach magnet. But
I mean, it's always a limitation of time again.
Yeah. But what can you do?
I'm happy to spread the knowledge, but if you feel we can provide an accurate summary of the argument in the next 5 or 10 minutes, we can definitely go there. Or if you feel like even that would not do it justice.
Well, I could do the quick, I told you there's the original Bell argument, and then there's this argument that Greenberger, Horn, and Zeilinger came up with, which is even quicker and nicer. And I can do it in 10 minutes anyway, if you don't mind. I mean, it's your podcast. I would love to.
We are here all night.
Good. Yeah. Okay. So let me just do this very quickly again. Maybe you can go there if you want more details. But the idea is there's certain things you can do in a lab. And this is, again, something that Einstein didn't think about, that David Bohm did think about, and that Bell picked up from Bohm. So there's a whole story here. But it's something we call doing spin measurements. And you don't need to understand anything much about them, except that when you do a spin measurement on a particle, in the standard way, you have a magnet called a Stern-Gerlach magnet. And the Stern-Gerlach magnet, that's what these were for, has a funny geometry. So there's a north pole and a south pole to this magnet, but they're not geometrically the same. The north pole is kind of pointy and the south pole is flat. Mm-hmm. And the result of that, just classically, is that if you think of the magnetic field lines here, they change from top to bottom, right? They're not uniform. And the effect of that is that when you send a particle that has a magnetic moment, so is itself like a little magnet, it'll be deflected by that field. If the field were uniform, it typically wouldn't be deflected, but because it's stronger in some places than others, it's deflected. And quantum mechanically, the prediction is, this is not a classical prediction, that for certain particles, so-called spin half particles, every particle will either be deflected up toward the pointy part or down away from the pointy part by the same amount. So this is whereas classically there's a continuum, quantum mechanically things are discretized, either it's deflected up or down. So to do one of these experiments, there are only two pieces of data that need to be recorded. What direction was the magnet pointed? Because you can rotate the magnet in space. You can point it any direction you want. And was the result up or down? Spin up or spin down? Now, the first thing that what Einstein noticed, if we go back, this is the Einstein, Podolsky, Rosen paper. He wasn't looking at spin, but he was looking at other cases, is that for certain quantum states, you get this following, just with two particles, you get this following funny thing, that the quantum mechanical prediction, if you ask, will this particle, suppose I'm going to check them both in this direction, call it the Z direction. If we check for spin of both these particles, here's Alice and Bob is way over here. It's 50-50 whether she'll see up or down. It's 50-50 whether he'll see up or down. If they just sit there in their labs and you're sending out these particles, they'll just see a random set of ups and downs. No pattern at all. But when they get back together and compare their results, they'll notice that there's a correlation. Whenever Alice got up, Bob got down. Whenever Alice got down, Bob got up. So each can predict, even though at the beginning of the experiment, neither can predict what they're going to see. When Alice gets her result, she not only gets her result, but she's now in a position to accurately predict what Bob saw. So those things are called EPR correlations, perfect correlations. They allow the results of one experiment over here to give you information about the results of another experiment over there. Now, Einstein didn't think there was anything particularly spooky about that, and there isn't anything particularly spooky about that. As people say, you take a dollar bill and rip it in half and put each half into an envelope and send one envelope to Alice and one to Bob. And they know how you did that, but you kind of shuffle the envelopes. So they would say, well, it's 50-50 whether I get this half or that half. But once I open my envelope, I know what the other one gets. Nothing spooky about that. That's what we call updating, right? That's this Bayesian updating. I get new information. That's information about what happened in my lab. And also because of how these things were set up, it's information about what's going to happen in Bob's lab, right? Nothing spooky at all. What would be spooky, EPR pointed out, is if you said, look, it wasn't determined what Alice was going to see until she opened her envelope. It's not that she didn't know, but it wasn't even determined, that something fundamentally chancy happened. Right? That Alice and Bob were actually sent identical envelopes with identical contents, right? Not the left side to Alice and the right side to Bob, but neither left nor right to Alice and neither left nor right to Bob. And furthermore, when Alice opened her envelope, magically her opening the envelope forced it to become either right or left. And then even more magically, that also forced Bob's half way over there to be the opposite. Okay, that's spooky. That's really spooky. That's spooky action at a distance, right? So there's the God plays dice part when she opens her envelope, but there's the spooky action at a distance part by the fact that Bob always sees the opposite. Now, Einstein thought that was ridiculous, right? Why would you believe that? No reason to. What you should assume is that it's predetermined from the beginning when you put them in the envelopes, which was the right half and which was the left half. And all you did was send this thing out. So that would explain this phenomenon. If you shuffle them, it would explain why it's 50-50 on each side. And it's easy to explain these correlations. Nothing spooky at all. What Bohr is insisting, because he's insisting on the completeness of the quantum mechanical state, is that there must be spooky action at a distance in a situation where you don't need it. That's why he was so upset. That's what the EPR paper was about. Now, let's change the situation a little bit. Again, this is kind of jumping over what Bell looked at to GHC. So now we've got three labs. We've got Alice, we've got Bob, and we've got Charlie. And again, they're all separate, and we can separate them as far as we want. Here's Charlie, he's in white. Separate them 100 billion miles. Doesn't matter. The theory doesn't care how far apart they are. At the center, we have a device that creates triples of particles and sends one off to Alice, one off to Bob, one off to Charlie. Okay? And we're going to assume that Alice and Bob and Charlie could in principle set their little magnets in any direction they want, but we're going to restrict them. So either they only each has two choices. They either set it in the z direction, which will be this way, or in the x direction, which is at right angles. So either z or x here, either z or x here, either z or x here. So, okay, three things. There are two choices. So there are 8 possibilities globally. Maybe they're all z's, maybe they're all x's, maybe one is 1 and the other 2. Okay, there are 8 ways you can do that. Yep. They are free to choose whichever direction they want in whatever way they want. They can use random number generators. They can go off the digits of pi. They can do it on the number of shares of stock sold on the stock exchange. They can look at the light from distant quasars, which has been done for various reasons. Okay, but anyway, so effectively, these are random selections. Now, what's the data? So here's the question is, could you prearrange the outcomes of these experiments to get the quantum mechanical predictions? So I hope everybody's with. So what are those predictions? Well, there are 2 of them. If they all choose X, well, I guess I usually do Z. I don't know. It doesn't matter. If they all choose Z, let's say, they all happen to, let's let Z be up. So they all happen to pick that they're going to check for spin in that direction. Quantum mechanics predicts with certainty, with absolute 100% certainty. So this is going to be perfect correlations. There will be an odd number of up outcomes. Now, it could be 1, it could be 3. It doesn't tell you which of those it'll be, but it says you'll never get 0, you'll never get 2, right? So just stop there and think, okay, wait, so if they all check X, there'll be an odd number of X outcomes. So that means if I know what Alice got and what Bob got, I can now predict with certainty what Charlie got, right? So these are these perfect EPR correlations. Is there anything spooky about that? Well, not if it's predetermined from the beginning. It's nothing spooky. Maybe it's predetermined from the beginning. They'll all get up if they check X, or that Alice will get up and they'll get down. The other 2 will get down. If you predetermine it, that's fine. But these are these perfect correlations. If you say something chancy happens to Alice, then the question is, but then how do Bob and Charlie, how do their particles know what Alice's did? That's spooky action at a distance. Okay, so prediction. If they all check Z, there'll be an odd number. The other case we care about is what if one of them checks Z and the other 2 check X, right? Now, there are other cases than that, but we don't care about the other cases. So 1Z, it's either all Z's or 1Z and 2 X's. The 1Z and 2 X's can happen in 3 different ways, because it could be Alice who checks Z, it could be Charlie, it could be Bob. But here's the prediction of quantum mechanics. If it's one of those cases, for sure, 100%, there will be an even number of up outcomes. Could be 0, could be 2, but an even number, always. And again, if I know 2, I know what the last one did. That's all you have to remember. Now you say, I don't want spooky action at a distance. That means I have to predetermine all of these outcomes. Can I predetermine them so that no matter what, this is like, no matter which 2 you pick, I lift my hand and they're different colors. No matter which ones they pick, it'll work out okay. Okay? And the answer is you can't. And this is mathematically, and it's kind of easy to see mathematically. Although, can I use your pen and paper and just draw something that if there's a, yeah, good. So here's the diagram of the situation. This is, as far as I know, was invented by David Merman, this way of presenting it, and it's really lovely. So I'll just give you this diagram. And the reason why I want to do this is because I really do want people to understand this argument's not hard. It's not really obscure. ZA, ZB, BC, D, B, X, A. So
let's show that. Yeah.
See this? It's just this nice little kind of structure, truss structure. I've got ZA, ZB, ZC, and this dotted line. So this represents Alice choosing to measure Z, Bob choosing to measure Z, Charlie choosing to measure Z. And then here's Charlie C, Bob, Charlie X,
Yeah.
Bob X, Alice X.
Mm-hmm.
So the first prediction was if they all measure Z, there'll be an odd number of outcomes. So that if I imagine an outcome, I predetermine an outcome by writing U or D in each circle, I need an odd number of U's written in these three. But if they choose this or they choose this, the solid lines, which is 2 X's and 1 Z, there has to be an even number of U's, an even number of U's, an even number of U's. So now it's a very clear question. Can I write the letter U and the letter D in each of these circles in such a way that there are an odd number of U's along here, even along here, even along here, even along here, right? That's a really clear question. Now, first, let me just try, right? I'll just give it a shot. Let's begin here. We want an odd number of U's. It's got to be 1 or 3. Again, the easy thing, make it 3, because then I don't have to make any further decisions. So I'll just write U, U, U. Okay, so at this point, if it happens that they all check Z, we're okay. They'll get an odd number. The central one, there's nothing really to force that. I'll just put a D in there. But now, my other constraints start to bite. So I need an even number of U's along this row. I've got 1. That's a D. I'm forced to put a U here. So I've got 5 out of 6. Only this last circle, but I'm screwed, right? Because to make it even along this row, I have to put a U, and to make it even along that row, I have to put a D. That doesn't work, right? Doesn't work. Now you might say, well, do it some other way. Maybe there's some way to make it work. And then David Merman gave this lovely argument. He says, look, it can't be done. How can I show you it can't be done? It's an argument by reductio ad absurdum. Suppose for a minute there's some way to do it. So suppose there's some way to write U's and D's in those circles that satisfy all those constraints. Okay. Pick up the ones along the dotted row. That has to be an odd number of U's. Throw them into a hat. Then pick up along this row. That's an even number. Throw them in the hat. This row, even. Throw them in the hat. This row, even. Throw them in the hat. So what have I got in the hat? Odd, even, even, even. I have an odd number of U's. That's all the math involved here. That an odd number plus an even number plus an even number plus an even number is an odd number. I have an odd number of U's in the hat. But I picked up every disk twice because every single one of these circles is intersected by 2 of these lines. So no matter how I put U and D in these circles, I can't have an odd number of U's in the hat, which means there is no possible way to predetermine these outcomes locally so that what Alice does doesn't affect Bob, what Bob does doesn't affect Alice and Charlie, right? No local theory in Bell's sense can make these predictions. Quantum mechanics makes these predictions. The world fulfills quantum mechanical predictions. So no Bell local theory can account for this. So the true physics, whatever it is, can't be Bell local. That's the argument. And there are not many moving pieces to this argument. It's not like, having to check Andrew Wiles' proof of Fermat's last theorem where it's 400 pages long and nobody can, you can do this at home, right? You can check out yourself at home. You can't do it. So that's the kind of thing when you say Bell proved that certain phenomena cannot be predicted and explained by any relativistically local theory. This is an example. And so it tells you something goes faster than light. There's some causal connection, right? There is some way that what Alice does, her choice, or Bob or Charlie, has to have some influence on the outcomes of some of the other experiments. Now, if you add in this foliation that I talked about, and you say, well, how can I do this? How can I write down a theory that does this? Okay, add in this foliation. Then one of the 3 experimenters will be the first. And you can write down a theory in which the choice of the first experimenter has influence on the later ones. And you can work it, and you can write it down, clean mathematics, it all works out, but it's non-local. So that that's the short story. It's not, and it doesn't take that long to explain. That's why it's a shock. As I said, I gave this talk, I gave exactly this proof. And, a guy trained in astrophysics said, we never went over any of this in our texts. How long does it take to do? Right? Why doesn't every physics student understand this? Because they don't want to talk about it. Because as soon as you talk about it, then there's some kid's going to put up their hand and say, but how do you explain this?
I'm glad we took that extra time to walk through the argument, and I'll definitely provide a link to the full in-depth explanation as well. We can go on for hours and hours about this, but I'm glad we actually got a good teaser into Bell's argument. Okay, who would have thought actually the inventors of Lego would have never thought that they would have used Lego to talk about Bell's theorem and quantum non-locality? What masterpiece do you think I've built with my... Yeah.
I'm afraid I can't interpret it.
It's a superposition of multiple interpretations. And you just have to make it materialize into one state.
Yeah, I mean, we could have gone on about the... I'll just mention this because people will hear this all the time. The term superposition is used a lot in talking about quantum theory. Mm-hmm. It also... if you understand what's meant by it, it's not so puzzling. It's not people say, oh, it's just, in mathematically, it's very clear what it means. People just throw the term around, and it's a bit they throw it around in a way that would naturally be quite mystifying to anybody trying to follow what they're saying. And it's not so bad.
I'm just intentionally throwing around these terms and sending you down these rabbit holes, right? Next, I'll throw quantum entanglement or something else, but we need to stop at some point.
Yeah.
All right, so let's move into some of our closing questions. What are some books, movies, role models that have strongly influenced you in your life?
Well, I mean, among the books that strongly influenced me were certainly, you're not going to be surprised, John Bell's. I mean, there's a collection of some of his papers called Speakable and Unspeakable and Quantum Mechanics, mm-hmm. which again, if anybody here, you should understand it's good that it's not a book. It's a collection of papers that are written at all different levels of technical precision. And some are written really for a lay audience or for an audience of cosmologists who haven't thought about this. So if you look through that book, no matter how much background you have, you should be able to find some paper that you can follow. I don't want to say all of them. If you have technical expertise, he'll go into all the details in some places, but in some places he's very careful to just give you the picture. So that certainly in this had great influence in me. People interested in this, again, who have a philosophy background, probably the first really good book to do this well was David Albert's book, Quantum Mechanics and Experience. I mean, David has a fairly unique style. You have to get a little used to the writing, but he's also very deeply concerned with understanding what's going on, right? Not burying it under unnecessary formalization. So you might find that useful. For this stuff, I can't say movies have had any particular, movies tend to just love the mystification, or they have some plot device that they can't really explain with real physics. So they just wave their hands at quantum mechanics and say, oh, that takes care of it.
But beyond just in life, any movies that you would recommend that had a huge influence in your life?
There are movies I very much like. I mean, I'm actually a big fan of movies. When I was, my roommate in college was a film major, and we actually co-founded and ran a movie series, Davenport Film Addicts, where we showed a lot of stuff. Well, I mean, old stuff that wasn't popular, just more art film. Lots of films like that, but it would be too long to go into them and explain why. I mean, people watching this will understand that I think 2001 is a brilliant piece of filmmaking. I think Citizen Kane is a brilliant piece of filmmaking. It's not supposed to be a controversial claim, but every time I see it, I'm going like, wow. But these are mostly at the level of just aesthetic appreciation of cinema. And again, in the same way, I mean, lots of books for different reasons, just purely aesthetic reasons. One book I guess I read that maybe had more of an intellectual influence on me was Huxley's Point Counterpoint. I found a really nice characterization of characters with different ways of thinking about the world and living in the world, and how they're, they clash into each other. And it was very interesting.
I think that's a great list. Tom Lehrer once sang, "Once the rockets go up, who cares where they come down? That's not my department," says Werner von Braun. You have undertaken this mighty task of making many branches your department. You are tackling some of the most fundamental questions, the foundations of physics, which invariably, I think, start involving all these different departments. In that spirit, what would you like your legacy to be?
Well, I do care where things come down, right? I mean, I've spent certainly over half my career doing nothing but promoting what Bell did, trying to explain it to people, encouraging them to read it, to understand it. So that's not, and I founded the John Bell Institute for Foundations of Physics with a very practical aim in mind, which was to try and solve this problem that people worrying about these problems don't have a natural institutional home in the present university. If you want to do foundations of physics, you're not going to have luck getting a job in a physics department. And that's what happened to David Albert. He has a degree in theoretical physics. His first job was in a physics department, but for what he was doing, he had a better fit in a philosophy department, which is kind of sad. It's like the fact that so much of Aristotle and Plato was only saved because people in the Arabic tradition saved the manuscripts, right? Yeah. Not people in Greece and Rome. Yeah. They saved it, and eventually it came back, and somehow foundations of physics has been more or less driven out of physics departments, and it's kind of hiding around in places. It would be nice if it had a home. What I've been working on for the last few years is trying to make that a physical reality. For people interested, there's a website, johnbellinstitute.org. And for people really interested, we're trying to raise money for the practical purpose of actually creating a physical location. I mean, the Institute exists as a collection of individuals. And you can see on the website how scattered we are in all kinds of ways, scattered across the globe, scattered in terms of our departments. My present thing I've been working on for some time is to try and literally build a physical place devoted just to work in foundations of physics, where workshops in summer schools and people could come and individually work on their own material and have other people around. I have no idea whether I'll be able to do that. It's run into some snags. There are some other things that have happened that have been hopeful. I'm actually have a GoFundMe trying to raise money for it. I'll know in a few years whether that will be a legacy. If that were, that would be the most important thing I think I could do, because, especially young people interested in this are more or less on their own, and they need support, and they need to feel like there is a support system, and there isn't one now.
I believe one of your college professors had told you that not even if you're Immanuel Kant do I recommend that you go into grad school for philosophy.
Yes.
And the fact that you are trying to change that for people in college today and try to provide a home for foundations of physics, I think that's definitely a rich legacy that you leave behind. Even if you don't get the physical structure, I think it's just the work you're doing now itself is already a rich legacy.
Well, it's really important. I mean, so I was very, very lucky, in literal, just blind luck. My first job was at Rutgers, and Shelley Goldstein was in the math department at Rutgers, and I could have gone my entire career at Rutgers and never met him because it's a very big campus. But by kind of happenstance, I met him. And anyway, Shelley, early in his career, found two other people, Detlef Dürr and Nino Zanghi, who were became interested. They didn't even start out necessarily interested in quantum mechanics, but became interested. Nino did, not so much Detlef. And the three of them could support each other. I mean, they were kind of just alone. Hard to get anything published in a physics journal. Many physics journals, they were doing stuff on pilot wave theory. Literally, they'd be desk rejected. We will not publish anything on this topic. They had to fight editors. They had to fight referees at every point. They had each other to rely on. And if they didn't, I don't know, how far they could have gotten. So yeah, there's solidarity among people with these interests is very important. As far as what I was, the suggestion for me was not to go into philosophy just because, he said there are no jobs. I mean, the job situation is very difficult. And one thing I certainly can't aspire to do is exactly solve that. Except the only possibility would be to convince physics departments that, maybe you should have one person in this big department who's actually interested in teaching these issues. That would give people some more hope to surviving in academia. But I can't do that directly. I can try and do what I can just so people feel like there's a functioning collective of people interested in these issues who are talking to each other.
I hope so. And I think it's interviews, episodes like these that hopefully start sparking the interest slowly, one step at a time. Final question. What is the meaning of life, Tim Maudlin?
Well, I think there's no, there are many answers to that, and there's no answer to that. The universe does not exist for any particular purpose. I think that's what Galileo discovered. That's what telescopes discovered. I mean, nobody can look at what we now know about the physical universe, I think, and think it was designed for some reason, because it's just too random and there's too much, and we're just kind of a little piece of dust in some suburb of some typical galaxy. If you're looking for that kind of meaning, or why does life exist? Well, it's kind of an accident. I mean, there were some very lucky accidents that life got started and that evolution went, and then kind of a lucky accident for us that a big meteor came and wiped out all the dinosaurs, or we wouldn't be here. Okay. If you're looking for that kind of meaning, I don't think there is one. If you're asking the more important question to me, what would make my life feel significant or meaningful? Then there are lots of answers to that. Helping other people, creating art, trying to understand things. I mean, all of these are clearly significant. They mean more than making money, for sure. Everybody can find things to do that anybody would say you made a difference, you made a positive impact on the world. There are lots of ways to do it. And nobody needs my advice. I think each individual has to discover within themselves what attracts them, what draws them, what they're willing to spend time at, what they're good at, various things that would lead you in different directions. There's not just one direction for it. But God knows there's more to life than making money. If that's what you think the meaning of your life is, then you've gone off in the wrong direction, right? There are lots of other directions you should be going into.
I think that's a great meaning. Professor, thank you so much. If people want to connect with you, find out more about your work, find out more about the foundations of physics, get involved with the John Bell Institute, where can they go? Where can they find you?
Well, the Institute, again, has its own website. I mean, I'm there as the director, but lots of other people are there. I guess I should warn people, somebody set up a very nice website for me personally, just as a favor, but I don't know how it works, and people tell me the email thing there doesn't work, so you can't get me that way.
Yeah,
I have email and so on people can find. I'm not sure I want to encourage. I mean, I do get emails where the best, I'm afraid to say that the best judgment is just not to respond to them, because sometimes you respond and you get drawn down various rabbit holes with people that you wish you'd never started, because they can be very persistent. So I can't sit here in all honesty and say, if you just shoot me an email, I'll respond. I mean, I do kind of look and say, is this something I could easily respond to? And does this look like a person who might benefit from what I have to say rather than just get upset if I tell them that they're confused. And I do have to make those judgments. I mean, I don't want to offend people, but that's just the situation. You can get into bad situations of bad interactions with strangers.
Well, I'm glad you responded to my email. I don't know if that was prearranged or you played dice with that email. But
yeah. I mean, look, you sent me an email and I read it and I kind of looked and I said, yeah, okay, yeah, that's fine. I mean, I've had some other people ask me to be on a podcast, and I looked at their podcast and I said, no, I don't. I just don't want to be on this podcast. I think you're not doing it right. Sometimes they sit there and people are spouting just complete nonsense and they don't push back and they don't, and I don't think, podcasts, like every other little bit of new technology, they have good uses and they have bad uses. So you have to make judgments.
Well, I must say this conversation, and even just doing the research for this conversation, it taught me so much that in my eyes, it's already a success, at least in my life, like much richer before I started. So Professor, I must say, thank you so much. It was an honor talking to you.
Okay, thank you.